You've probably heard of magnesium as the stuff in your multivitamin or maybe something you sprinkle into your bath when your muscles are sore. It's got a soothing reputation, calming, relaxing, healing. But there's a twist. Magnesium can also catch fire and burn so brightly that it can literally blind you. Not exactly the gentle mineral spa day image you were expecting, right? Today we will be talking about the double life of magnesium, the element you chose in the poll, a calm essential nutrient on one hand and a dangerously reactive metal on the other. In this episode we are going far beyond the Epsom salt myth. We'll trace the roots of this brilliant element back to ancient Greek lands and a bitter well in England. Follow the scientist who first teased it from rock and discover why it is just as important for your muscles as it is in fireworks, flares and fighter jets. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic table and also do experiments. And if you like these type of videos and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, if you can't get enough of chemistry, make sure to check out our memberships. And if you want to influence next week's element, make sure to fill in the poll in the community tab. Now inside this cube we've got a beautiful unicorn element that shines pink, and you've never seen anything like this, right? Now, of course you have, because it's another gray metal, but it is quite a big chunk though, and for fun I've also have some samples from my lab outside the cube for comparison. So here I got some magnesium balls and some magnesium band that we will set on fire later. Now the bands seem to be a little corroded, but the balls seem to be about the same color as in the cube. Now if you want to collect the elements like we do, or you want to have just one specific cube with magnesium in it, or another element, click on the link in the description, use the promo code so you can get a 10% discount, and you will also be helping out our channel. Magnesium gets its name from Magnesia, a region in Greece. This area was known in antiquity for stones and minerals with almost magical properties. One type of rock from Magnesia was a black mineral that could attract iron, what we know today as magnetite. That gave us the word magnet. Now another substance that was found there was a white powdery earth that didn't attract metals but had a curious effect on its own. This white mineral became known as magnesia. Healers in the ancient world found magnesia could be used as a laxative or an antiacid, soothing upset stomachs long before anyone knew about elements or the periodic table. Though they didn't know it, they were using a compound of magnesium. The element itself was hidden within that earthy white powder, centuries away from being isolated in pure form. The name stuck. Magnesium, magnetite, and even manganese, another element from a magnesium mineral, all owe their names to that Greek region and the confusion of ancient minerals that needed sorting out. So let's fast forward to the 17th century England. The year is 1618 and an English farmer in the town of Epsom makes an interesting discovery, with a little help from his cows. The cows refuse to drink from a particularly bitter tasting well on his farm. The farmer noticed something odd. That bitter well water seemed to help heal scratches and rashes on his cattle's skin. Curious people began to evaporate the mineral water from Epsom and found it left behind crystallized salt. These crystals became famous as Epsom salts, named after the town. Word spread that Epsom salts could soothe skin irritations and when dissolved in bathwater seemed to relax aching muscles. It became a popular home remedy and a spa treatment long before modern chemistry explained why. While Epsom salt was making a name for itself in folk medicine, scientists were beginning to ask deeper questions. What was this magnesia exactly? What was it made of? In 1755, a Scottish physician and chemist named Joseph Black conducted a series of experiments that inched closer to magnesium's true identity. He studied a substance called magnesia alba, literally white magnesia, a lightweight white powder now known as magnesium carbonate. By heating magnesia alba, Joseph Black found it lost weight and gave off a gas. We now know this gas was carbon dioxide. The residue left behind was a caustic solid, magnesium oxide. Through these tests, Black deduced that magnesium alba was not the same as lime, calcium carbonate, as many thought, but contained a different basic substance. In effect, he recognized magnesium as an element distinct from calcium. Even though he didn't isolate the metal itself, he identified the presence of a new earth. This was a huge step. Magnesium had been scientifically discovered as a unique element on paper, even though nobody had seen pure metallic magnesium yet. The honor of first isolating magnesium metal goes to the famous chemist Sir Humphrey Davy in 1808. Davy, a true pioneer of electrochemistry, was tinkering with a new technology of the day, the electric battery, to break apart chemical compounds. Davy had already used electricity to isolate sodium and potassium, and magnesium was next on his list. He took a compound of magnesium, a paste of magnesium oxide mixed with mercury oxide, and subjected it to electrolysis, basically zapping it with electrical current. Sure enough, this process coaxed tiny droplets of a shiny metal out of the compound. That shiny metal was elemental magnesium. Davy originally proposed calling it magnium, but eventually the name magnesium prevailed. Humphrey Davy had unwittingly laid the groundwork for lightweight metal alloys and camera flashes of the future, all with a jolt of electricity and some clever chemistry. In the years that followed, methods for obtaining magnesium improved. In 1831, French scientist Antoine Bussy found a better way to produce magnesium in sizable quantities by reacting magnesium chloride with potassium, yielding larger globules of the metal. Now, as the 19th century progressed, magnesium went from a laboratory curiosity to a material people could actually use. By the late 1800s, it was being utilized in one particularly flashy application: photography. Early photographers discovered that powdered magnesium, when ignited, burns with an intense white light, perfect for illuminating a scene in a split second. If you've ever seen those old-time photographs where the photographer sets off a bright flash with a puff of smoke, that was magnesium power lighting up the room. Magnesium's brilliant flame literally helped capture history on film. Moving into the 20th century, magnesium found its way into more and more uses, especially as scientists and engineers learned how to produce it on an industrial scale. For instance, extracting it from seawater or mining minerals like dolomite. Magnesium's story continued through 2 world wars, where its lightweight strength made it valuable for building aircraft, though its flammability also made those planes a bit more dangerous if they caught fire. The Germans coined the name electron for their magnesium-aluminum alloy used in the aircraft in World War I and II. By mid-century, magnesium was firmly established as an important metal in technology. So let's get back to the magnesium balls and the magnesium band. If you have a piece of pure magnesium metal in your hand, like we got here, you'd notice a few things right away. First, it's a lightweight metal. In fact, among common metals, magnesium is one of the lightest. It's about 2/3 the weight of aluminum by volume. Now, a block of magnesium almost feels featherweight compared to steel or even aluminum. This lightness is a big reason why magnesium is so useful. Imagine building airplanes or car parts with a metal that adds much less weight. That's a huge advantage. Magnesium in pure form is a silvery gray color, like in this cube, kind of shiny, but it quickly tarnishes to a dull gray as it reacts with air, like with the magnesium band we got here. Now, it's not a super hard metal. It's relatively soft and can be cut or filed with some effort, though in some forms it can be brittle, breaking if you bend it. It depends on how it is processed or alloyed. If you rub a freshly sanded piece of magnesium, it might even leave a gray powdery mark on your hands. That's some of the metal turning into magnesium oxide on contact with moisture and oxygen. Magnesium loves to react with oxygen. On the periodic table, magnesium sits in group 2 among the alkaline earth metals, like calcium and barium. These metals all have 2 electrons in their outer shell, which they are eager to give up in chemical reaction. That means that magnesium typically forms a +2 charge when it becomes an ion. So what does this mean? Well, practically this makes magnesium highly reactive, but not in a dangerous, explosive way at room temperature. It's more subtle. For instance, if you expose magnesium metal to air, like we did with the magnesium band, it will slowly react with the oxygen to form a very thin protective coat of magnesium oxide on its surface. Now, this oxide layer actually sticks to the metal and prevents further rapid corrosion, a bit like aluminum's protective oxide layer. So while magnesium metal does tarnish, it doesn't instantly crumble to powder. The oxide is like a microscopic armor. Now heat things up and magnesium shows its true reactivity. If you get magnesium metal burning, it reacts with oxygen with a ferocity that is hard to believe until you see it. Magnesium strips or powder will burn with a brilliant white flame. It's extremely bright, so bright that it was used, as mentioned, for flash photography. And it emits a lot of ultraviolet light, the kind that can harm your eyes. Now that's why anyone doing the classic magnesium ribbon burn experiment, which we will do later in the lab, is told to don't stare directly at the light. It's like staring at a welding arc or the sun. The product of that burn is magnesium oxide, a white ash. Interestingly, magnesium burns so hot that it can even snatch oxygen from other molecules. For example, if you try to extinguish a magnesium fire with water, the magnesium can split the water, H2O, to grab the oxygen, producing hydrogen gas, which, you guessed it, can also ignite. Likewise, magnesium can steal oxygen from carbon dioxide. This means that water or CO2 fire extinguishers don't work on a magnesium fire. In fact, they can make it worse. The proper way to put out a burning magnesium fire is with sand or with a special Class D fire extinguisher that smothers it without providing oxygen. At normal temperatures, magnesium doesn't react explosively with water. It reacts slowly. Drop a piece of magnesium metal in water and not much happens right away. Over time, you might see a few bubbles of hydrogen on its surface. Magnesium is a good conductor of electricity and heat, as most metals are. It's not as stellar a conductor as copper or silver, but it does the job. This is why magnesium or its compounds can play roles in electrical applications or heat-bearing structures. One thing magnesium is not good at is hanging onto magnetism. Despite its name origin, magnesium metal itself is only very weakly magnetic, technically paramagnetic, which means it doesn't retain magnetism and is only faintly attracted to strong magnets. In nature, you will never find shiny chunks of magnesium lying around. Magnesium is always found in compounds. Combined with other elements, it's abundant though. Magnesium is the 8th most abundant element in the Earth's crust and a major component of the Earth's mantle, the rocks deep underground. It's also dissolved in seawater in large amounts. If you evaporate seawater, you get lots of salt, sodium chloride of course, but magnesium salts like magnesium chloride are the next big fraction. In fact, magnesium is the 3rd most abundant element in seawater after sodium and chlorine. That bitter taste in ocean water? Magnesium has a hand in that. Magnesium salts tend to taste bitter. The abundance is why we can extract magnesium from seawater commercially. Companies actually take brine or seawater and chemically precipitate magnesium compounds out, then refine them into magnesium metal. So while a bar of magnesium metal is not something you stumble upon in nature, the ingredients to make one are all around us and in great supply. So let's do an experiment now that showcases magnesium's dramatic flammability, one of its hallmark properties. This is a classic burning magnesium demonstration, a favorite in chemistry classes and YouTube videos because it is simple yet spectacular. Now, safety comes first, so imagine we're doing this in a controlled lab environment, currently our garage. So here we have a strip of magnesium band from earlier, and we put that in a contraption. Now, we need to flame this with a Bunsen burner, but we used a high-temperature lighter, which also worked. You can also dim the lights if you want, because you are going to produce some serious brightness. Now, at first, magnesium has to heat up. It doesn't catch fire immediately like a piece of paper would. Remember, magnesium has that oxide skin that needs to get hot enough to break through. But once it reaches ignition temperature, the magnesium strip ignites and burns with an intense white flame. Now the light is so bright that it illuminates the whole room if we would have darkened it a little bit, and it would cast sharp shadows. It's a white light rich in ultraviolet rays. In fact, it is painful to look at directly. The reaction is blazing hot, easily reaching temperatures of 2000 degrees Celsius over 3600 degrees Fahrenheit. For a few brief moments, the magnesium burns, and then, as it consumes itself, the flame subsides. Now what is left? The one shiny strip is now a crinkly, brittle, white ash. That ash is magnesium oxide, the product of magnesium reacting with oxygen in air. If we touch it after it cools, it's powdery and stark, white, completely different from the metallic strip we started with. We just witnessed a combustion reaction that looks like this, releasing a ton of energy in the process, the heat and light. Now, magnesium was used in flares. For example, a magnesium flare can be seen from great distance because of that bright light. Even today, some emergency flares or pyrotechnic flares contain magnesium for brightness. Those trick birthday candles that relight themselves, guess what? A tiny bit of magnesium in the wick helps them spark back up after you blow them out by igniting on the residual heat. One of the most significant uses of magnesium is in making alloys, mixtures of metals that are lightweight and strong. For example, magnesium is often combined with aluminum in small amounts of metals that create alloys that are lighter than pure aluminum, but still durable. The aerospace industry took an early interest in this. As far back as World War I, engineers experimented with magnesium-aluminum alloys for aircraft parts to reduce weight. By World War II, the German Air Force was extensively using magnesium alloy, they dubbed Electron. It was used in engine components, gearboxes, and aircraft frames. The lighter the plane, the better it flew, and the further and faster. However, as we learned, magnesium in a plane had a downside. If the plane caught fire, the magnesium parts could burn fiercely. This led to some dramatic incident. Because of that, after World War II, magnesium's use in airplanes was a bit restrained, mostly limited to non-critical components or inside engine housing where it was less likely to ignite. In the 21st century, interest in magnesium for transportation is surging again. Why? Fuel efficiency. For cars, every kilogram saved in the car's weight can improve fuel economy and handling. Magnesium alloys are used in some car parts like wheel rims, mag wheels, engine blocks, and transmission cases. Yes, if you heard the term mag wheels on sports car, mag is short for magnesium. Early racing cars in the 1960s adored magnesium wheels because they cut down the weight significantly. They also sometimes caught fire in spectacular fashion if the brakes overheated. Seeing a pattern? Lightweight, but handle with care. Bicycle enthusiasts might also encounter magnesium alloys in high-end bike frames or components. The idea is the same: light frame, easier pedaling. Some laptop and cell phone manufacturers even use magnesium alloy casings to make devices robust yet light. That rigid premium feel, metal body on a laptop might well be a magnesium alloy. Magnesium's fiery talent as a strong reducing agent, remember it loves to give up electrons and bind with oxygen, is harnessed in industrial chemical processes. A prime example is the production of titanium metal. Titanium is another important metal used in aircraft, medical implants, and more. To get pure titanium metal, you have to reduce TiCl4. By that, you have to strip away the chlorine and add electrons to the titanium. Guess which element is often used to do that? Magnesium. Another chemical use is in the iron and steel industry. Molten iron often contains impurities like sulfur, which can make steel brittle. Magnesium can be added to the molten iron because it reacts with sulfur to form magnesium sulfide, which floats out as slag. This desulfurizes the iron, helping produce higher quality steel. Now we've seen how brilliantly magnesium burns, and humanity has definitely taken advantage of that. Fireworks often incorporate magnesium or magnesium aluminum alloys like magnesium to produce white sparks or increase the brilliance of explosions. Magnesium isn't just an industrial metal. It's literally a part of us and all living things. In fact, it's often said that magnesium is life's spark. Every cell in our body contains magnesium and needs it to function. It's the 11th most abundant element in the human body by mass, which is remarkable when you consider all elements that we have. Why is magnesium so important biologically? For one, magnesium is a key player in our muscles and nerves. When you move a muscle or when a nerve fires an impulse, magnesium ions are involved in the electrical signaling and the chemical reactions that make it happen. Magnesium works closely with calcium in the muscle cells. Calcium signals muscles to contract, and magnesium helps them to relax. If you don't have enough magnesium, you might experience muscle cramps or spasms because muscle fibers aren't relaxing properly. Magnesium is also crucial for our heart. It helps regulate heart rhythm and blood pressure. Magnesium is a cofactor in hundreds of enzymatic reactions in the body. Over 300 enzymes rely on it. It helps with synthesizing DNA and proteins. Given magnesium's vital roles, it's no surprise that we need to get enough of it in our diet. Food rich in magnesium includes leafy greens. Spinach, for example, packs a magnesium punch thanks to chlorophyll. Nuts, seeds, legumes, and whole grains. Despite its abundance in food, many people, especially those with certain diets or health conditions, might not get sufficient magnesium. Now, some studies and health experts suggest that a lot of adults have magnesium intake lower than recommended. This has led to magnesium supplements being common on pharmacy shelves. People take magnesium pills or powders for things like muscle cramps, better sleep, or just general nutrition. Doctors also use magnesium in medical settings. A famous one is using high-dose magnesium sulfite intravenously for pregnant women with eclampsia, dangerously high blood pressure with risk of seizures. Now, with all of that, you can see why magnesium has a healthy reputation. Now, let's take a look at Epsom salt. Epsom salt is magnesium sulfate heptahydrate, to be precise. But let's keep it simple. It's a magnesium compound. The lore is that soaking in Epsom salt baths will help the muscle soreness, aches, and maybe even draw out toxins, according to some spa brochures. People often assume that because magnesium is so good for muscles and cramp relief, somehow the magnesium from the Epsom salt will be absorbed through their skin and go straight to work in their aching muscles. It's a comforting mental image. You sit in the bath, magnesium ions sneak into your body and recharge your muscles like batteries. However, science really doesn't back this up. The skin is a pretty effective barrier. It's designed to keep things out, or we'd all swell up like sponges in the rain. While a tiny amount of substance can penetrate the skin for most minerals like magnesium, the absorption through an Epsom salt bath is negligible. Now, in plain terms, soaking in a magnesium sulfite water bath isn't a practical way to get magnesium into your muscles or blood. One dermatologist famously explained it this way, paraphrasing, "The skin is more like a brick wall than a sponge, so while an Epsom bath feels good, it's not delivering a medical dose of magnesium to your cells." Research on Epsom salt baths is surprisingly limited given how popular the practice is. The proven way to increase your magnesium is through diet or supplements, not through your skin. Your digestive system is built to absorb nutrients. Your skin, not so much. So why do so many people swear by Epsom salt baths for sore muscles? Well, a couple of reasons. First, warm water itself is therapeutic. A plain warm bath, even without any salts, increases blood circulation, relaxes tight muscles, and reduces stiffness in joints. It also reduces stress, which may indirectly help with muscle tension. So a lot of the benefit that people feel is likely from the hot water and the relaxation of the bath, not the magnesium. Second, there could be a placebo effect or a psychological comfort at play. If you believe something will help you, that belief itself can sometimes produce a perceived improvement in symptoms. And you know what? If a ritual like an Epsom salt bath helps someone unwind and their muscles feel looser afterwards, that's fine. It's just important to have a realistic expectations. It's not literally healing muscle fibers or magically refueling your magnesium levels. It is also worth noting that there is no harm generally in taking Epsom salt baths, as long as you are healthy and stay hydrated and the water isn't scalding. In fact, Epsom salt baths can help with certain conditions like dry skin or minor aches simply because of the hydrotherapy aspects. And if you enjoy them, by all means, soak away. Just know that the benefits are likely from hot water and relaxation, not the direct absorption of magnesium. So next time you soak in a warm bath after a long day, you might smile, remembering that those Epsom salts are the same magnesium sulfate that once wowed Victorian photographers and that powers your cells. You'll know that while they aren't magically healing your muscles, the element magnesium in them has a far bigger role in your life than you've realized. Now, if you think I missed anything, leave it in the comments. And if you like this video, make sure to like, subscribe, and hit the notification bell so you will never have to miss another episode.